Hi, I'm just starting to summarize some of the data for our meeting, and I've written a sort of summary report, and we have to probably discuss the arithmetic mean. That's basically the average, total gates divided by the number of gate incidents. And I by total gates, I mean dollars, and divided by the gate incident. And I calculated this at 83.83 with a standard deviation of 12.41. Using an arithmetic mean, and that's what I believe is probably intended by the legislator, is a fine way, an easy way to do it, but subject to being overly influenced by statistical outliers. In other words, you could have one fare at one gate at $160, and that could push your mean out. So I wanted to look at our data and investigate it. The standard deviation is a deviation from the mean if a normal bell-shaped curve is assumed, and that's what I'm looking at. How normally is our data distributed? Plus or minus standard deviations will include 68% of the expected observations will fall on plus one and minus standard deviation, and plus two plus or minus standard deviation, we expect to see 95.4%. So if we establish that we have a normal distribution and that our data is showing a mean lower than a mean of equal to about $85, or maybe a little bit more, but a mean not close to 91.50. Now, what I want to do is make sure that the people don't realize that the mean is an average, and around the mean, if the data is normally distributed, you'll have some data out here at $120 and some data down here at, I think the lowest is $29. So we've got, and maybe I should have cut out the statistical outliers, and we can do that after discussion. But this just shows you with normal distribution, and this is 0, but our mean would be, it'd be 83.83 using individuals, and if we took average weekly averages, it's about 87 plus. I'll do that in another video. So if you understand that we can expect to have a certain number of data points above 120 and a certain number of data points at 29, but as long as within this area here, which is about 68%, 38% either way, or close to 70%, if most of our data falls there, we've got close to a normal distribution, and our mean is just a standard average, and they can't just come to this point and say everything above this is above 85 you owe to these drivers, because that's not what the law reads. The law reads the average, or actually I used the mean when I read it. Okay, so then I started to ask myself, see if I can get this thing to move. No, I can't. Yeah, that's not moving for me. Come down here. Oh, there it goes. Now I come down here and I make some additional comment. Do we have a normal distribution? Using the computed mean overall and the derived standard deviation of YCC gate data distribution would look like the following. And below I've got an actual, I fit the data. And then I say, do we have a meaning that our average prices plus or minus scores, but these are not abnormal for the computed mean. To do this, I constructed a histogram. In other words, I took the lowest, I'll show you all these at the meeting, or I could actually do another video. I took a histogram where I took intervals from the lowest to the highest, and this is what they look like. So they look pretty evenly distributed. Here's 85, and there's, and there are some out here, and there are some down here. So this is one way to look at our data. How evenly is it distributed? And here's the mean of that we're computing with this, what they say, with 83.83 a good mean with a normal distribution around, I think it is. And then I took our 83.83 as a mean and our standard deviation. And this here is a computerized generation of a normal curve. And so if you compare that computerized generation, which draws out a perfectly normal curve, with an 83.83 mean and the standard deviation, it's not that dissimilar from what you see with the histogram. I hope that makes sense. And then to test our data, I did what they call a cumulative distribution function. You can read my stuff. I'll post it. But it means I rearranged all our gates, the 1,774 of them, and then I put them from the lowest to the highest, and I made them into 170, 100, 1 over 1774, and I added them, and that's what a cumulative distribution function is. If this was actually the area under this curve, the summed area, each of these would equal to 1. This is 1 right here. It's just that, we could do the calculus on it if we have to. But this looks pretty good also. I mean, it's derived from, it's a mirror of our histogram. And so then I did a computerized cumulative distribution function, and it looks pretty good. They don't look that dissimilar. Anyway, this is for the next section. I haven't done the I haven't done this particular spreadsheet yet. I'm just working on the one, but I will get to it over the rest of by the time I meet you guys on Tuesday. So would you take a look at this, and I'll attach the spreadsheet to this and send it to you. I'll put this up on YouTube, but private viewing only. So I hope you understand this analysis. So what I've got here is a Word document, which I can hand out in the summary. But as a backup, I have all my work on these two spreadsheets. So I hope that makes sense.